Hey everyone, today we're gonna discuss a problem that was bothering me the first time I heard about neural networks, and this question was why do they work? Because the whole idea of how they are created is, to be honest, not really complicated. And another idea why they work is what is complicated the most, because obviously we cannot say that this thing somehow knows, for example, how to understand the DNA sequence, how to understand the audio and understand that there is a bird in this audio, because it's just a formula, to be honest. So a few words about what a neural network is. It's a machine learning algorithm that is capable of learning almost anything. It's built on sigmoids. The sigmoid function is something like that. And one layered neural network is just this thing. It's a weighted sum of sigmoids with different weights. This V matrix represents weights, just as we were talking about in weighted mean. It's just a weighted sum of parameters plus some bias. So when we graph it, it looks something like that. So we have, for example, two inputs, two numbers. We pass them to all of the neurons. Those things are called actually neurons. They do sigmoids with them. Then we pass those sigmoids to the last neuron, and it also does his sigmoid with different parameters, and it's activated, and that's what we get from the neural network. And my statement right now is that this one-layered network, or this, whatever you prefer to choose, is capable of learning every function in the world that can be actually represented. Let's talk about what that actually is. What is a function that can be represented? One of the, from my perspective, best ways to show how a neural network works is to show the simple example. So we have an image of this beautiful cat, and we have a label that there is a cat in this image. And my statement again is there is a particular function that is multidimensional, really complicated, is not understandable by us because it's extremely complicated, but this function is capable of giving this label cat to this picture. And to understand it better, think about it this way. When you see this image of cat, what exactly makes you understand that there is a cat on this picture, or just I don't know, or a dog or a human? You look at little details. So what are those details? In this example, there is his mouth, his ears, his tail, his eyes, and due to all of those factors, your brain somehow understands that if we get, for example, those different fractures of an image to our brain somehow processes it, and then we understand that this image is a cat. So another statement is that we can approximate, so make a function that is almost like that is almost like a certain function with neural networks. What is approximation? For example, we have this function. Let's say it's hyper multi-dimensional, like 1,000 million dimensional function that is extremely complicated, but when we shrink it to 2D space, it just looks like that. So what do we mean by approximation? With a neural network, we can create, for example, something that looks like that. So those two functions are almost similar. And this similarity we can do again and again and again until we get almost this one. So our neural network has just represented an algorithm that creates a function that we used in the previous example when understanding what a cat is. So therefore, if any function can be approximated, then our neural network can learn just everything, if of course there is an existing function. Alright, the thing is, the proof of the theorem that neural network can approximate every function, from my perspective, it's not really convenient to place the whole proof in a single video. So what I'm about to do right now is to tell the basic understanding, to convey the basic understanding to you about this proof. And if you understood everything from it and you want to dive deeper in the proof of the universal approximation theorem, you can just visit a website, not a website, a scientific work. It's from 1989, as I remember, called Universal Approximation Theorem, just as stated here. And there a person just proves that this can approximate almost everything. So here is what I state, the point of UAC, Universal Approximation Theorem. So what is that? How it's done? We have three key things. Mu, it's our spotlight. Just think about it as a regular spotlight. It can separate one function from another function. So we have two different types of functions. For example, let's say linear and exponential. Those are entirely different. There is a spotlight existing that is blind to all of the linear functions and show us that a certain function belongs to a space of exponential ones. So that is a spotlight. It helps us understand that some functions are different from other functions, that some functions have a different property that other functions don't have. And I call it a tangible space. It's not exactly a mathematical term, but for me it seems nice, it seems concise. This is the space of functions, just a whole bunch of functions that can be approximated from our sigmoids. It can be zero, it can be everything in the whole existing world, we don't know, but let's say that it's a tangible space what we can approximate. And mu, big M, uppercase 1, is what we can touch, is that what our sigmoids cannot approximate. And another take is that m plus m is the whole bunch of existing functions in the whole world, so they are all existing functions. And the whole point of the theorem is that we say that sigmoid is discriminatory. That's a certain property of this function that says that the only possible spotlight that is blind to all the sigmoids is zero. So we cannot create a spotlight that separates some sigmoids from some sigmoids. Those all belong to a single space. Those cannot be separated by a certain spotlight only if the spotlight is zero. And then we say that if mu can approximate the tangible space but cannot approximate this intangible space, let's call it like that. So due to the other guy's theorem, there exists a different mu that actually separates this intangible space from our tangible space. And if such mu exists, so it basically from the because the sigmoid things are involved in the tangible space, because it involves, as I've said, everything that can be approximated from sigmoids. Obviously sigmoid can approximate it from sigmoid. So this uppercase M can be like there is a spotlight that is blind to this M but not blind to this tangible space, or vice versa. So there's M that separates uppercase M from N, and that is what we're looking for. If there is such mu, so all of the uppercase N's are zero. And we say that this mu must not be zero. And that makes all of them zero. So, and due to the fact that it involves sigmoids, the only mu that can basically have the sigmoid zero is zero. But we've stated that it is not zero. So that's it. That's what we're looking for. If non-zero can be blind to all of sigmoids, so if M exists, we can create mu that separates sigmoid from mu. They are zero contradiction because mu is not zero. So that's everything for today. Thank you.